Okay, let's dive right into this. Astronomers have just announced something that completely shifts how we see the cosmos. Imagine for a second that the entire universe is humming, not with sound, but with extra large ripples in the very fabric of space and time. We're talking about ripples that are constantly squashing and stretching the shape of space around us, right this very second. It's a galaxy-wide mystery that scientists have literally been trying to solve for decades, and we finally have a massive breakthrough to talk about in this explainer.
So, what exactly is the universe humming? Well, astrophysicists call it a low-frequency stochastic gravitational wave background. Now, stochastic is just a fancy way of saying it's a randomly determined background in. Think of it as a constant overlapping rumble of gravitational waves that pervades the entire cosmos. And these are extra low-frequency waves, meaning it takes years, sometimes even decades, for just a single wave to pass by us while traveling at the speed of light. And honestly, the stakes for this 2023 announcement could not be higher. As theoretical physicist Chiara Caprini perfectly put it, it's beautiful. A new era in the observation of the universe has opened up. You see, this wasn't just a sudden overnight discovery. It's the culmination of more than 15 years of incredibly meticulous, patient data collection by teams across North America, Europe, Australia, and China. They've essentially unlocked a totally new window through which we can observe the universe.
Section 1. Hacking the Milky Way. Which brings us to our cosmic detectives and the genuinely ingenious forensic method they used. We're talking about astronomers using what are called pulsar timing arrays. Because think about it, to detect a wave that takes over a decade to wash over the Earth, you can't just build a standard telescope. You have to essentially hack the entire Milky Way galaxy. To do that, astronomers turned to the pulsar. First discovered back in 1967 by Jocelyn Bell, a pulsar is the rapidly spinning core of a dead star. As it spins, it shoots out beams of radio waves that flash across our line of sight hundreds or even thousands of times a second. They're so incredibly regular that they act like highly precise cosmic stopwatches. So, how exactly do you hack a galaxy with these stopwatches? Well, the Nanograph team used massive radio telescopes, like Green Bank in West Virginia and the famous Arecibo Observatory in Puerto Rico, to monitor dozens of these pulsars over 15 long years. And they did this because if a giant gravitational wave stretches and squeezes the spacetime between us and a pulsar, the arrival time of those flashes will change by just a fraction of a second. We're talking a couple of hundred nanoseconds. By mapping the correlations of these tiny, microscopic delays across the sky, they literally turned our cosmic neighborhood into a giant gravitational wave antenna.
Section 2. LIGO versus pulsar timing.
Now, you might be wondering, didn't we already discover gravitational waves back in 2015? And we absolutely did, thanks to the LIGO experiment. But comparing LIGO to pulsar timing arrays is kind of like comparing a sports car to a freight train. LIGO relies on 4-kilometer-long arms built right here on Earth to catch high-frequency waves, these really quick chirps from star-sized black holes crashing together in a fraction of a second. Pulsar timing arrays, on the other hand, have arms that are the actual distances from Earth to pulsars hundreds of light years away. These galactic-scale arms are sensitive to ultra-low-frequency waves created by supermassive black holes, waves so immense they take years to just rise and fall. So, with all that data, how did the team know they'd actually found this background hum, and not just, random space noise? The answer is the Hellings-Downs curve. Way back in 1983, theorists predicted exactly how the nanosecond delays from different pulsars should correlate based on their distance from one another in the sky. When the astronomers finally plotted their 15 years of data, this exact predicted curve jumped right out at them. It's the absolute smoking gun of the gravitational wave background. Section 3. The Supermassive Black Hole Dance. Okay, so what is actually generating this massive cosmic hum? Right now, our primary suspects are supermassive black holes. We're talking about absolute behemoths, millions to billions of times the mass of our own sun, just lurking in the centers of merging galaxies. To picture this, imagine a buoy bouncing up and down in a busy harbor. That buoy can't necessarily distinguish the wake of one specific speedboat from another. Instead, it's just bobbing in the chaotic, overlapping chop created by countless boats moving in every direction. That is exactly what this stochastic background is. It's the combined, overlapping gravitational waves from hundreds of thousands of supermassive black hole pairs, all slowly spiraling toward each other across the universe. And the journey these supermassive black holes take to finally merge is a pretty fascinating sequence. First, as their host galaxies collide, something called dynamical friction drags the massive black holes toward the new galactic center.
Second is stellar hardening, where the binary pairs slingshots individual stars away, which loses them energy and draws them closer. Third, at the subparsec scale, gaseous decay takes over. This is where the black holes interact with a surrounding disk of gas that extracts their orbital momentum. And finally, they get close enough that gravitational wave emission becomes the main force dragging them into their ultimate collision. And the data heavily backs this up. When astrophysicists look at the observed dual AGN fraction, which is basically just looking at galaxies where both supermassive black holes are actively feeding on gas and shining brightly as active galactic nuclei, the data perfectly aligns with a baseline model for supermassive black hole binaries. It's incredibly consistent, and it strongly supports the theory that gas-rich, spiraling supermassive black holes are indeed our primary culprits for the hum.
Section 4, Cosmic Strings and Physics.
But hey, science is never fully settled, right? What if it isn't black holes? Could this hum actually be cracks in spacetime itself? If supermassive black holes aren't the sole cause, we might be dealing with something called cosmic strings. I know, it sounds straight out of science fiction, but it's a completely legitimate concept that extends beyond the standard model of particle physics. So here's the case for cosmic strings. They were originally predicted in the 1970s as theoretical one-dimensional defects, literal cracks in the universe caused by the rapid expansion right after the Big Bang. Picture these tiny loops of energy constantly wriggling around. Occasionally, they'd crack like a whip, sending out huge bursts of gravitational waves. Some physicists have pointed out that if we don't eventually start seeing individual black hole pairs pop out from future data, the relatively smooth signal we're observing right now might actually point to these exotic cosmic strings.
Section 5. A new era begins. Regardless of whether it turns out to be black holes or cosmic strings, we are stepping into completely uncharted territory here, and it has massive implications for how we understand galactic evolution. For astrophysicists, this discovery might finally solve the infamous last parsec problem. For a really long time, theorists were worried that when two supermassive black holes get about 1 parsec apart, which is roughly 3.2 light-years, they'd just run out of stars and gas to interact with, and awkwardly orbit each other forever without ever actually merging. But the detection of this low-frequency hum strongly implies that they do bridge that final gap. They get close enough to churn out massive waves and eventually collide. It's truly amazing when you look at it. This discovery represents the long, triumphant arc of modern astronomy. Back in 1915, Albert Einstein's math predicted that these ripples in spacetime should exist. Then, in 1967, Jocelyn Bell discovered the pulsars that would eventually become our galactic stopwatches. Jump to 2015, and LIGO catches the first high-frequency chirps. And now, in 2023, Nanograv and international teams detect the deep nanohertz background hum of the cosmos itself. It's literally a century-long relay race of human ingenuity. I want to leave you with this incredible thought to wrap up our explainer today. We now know for sure that the universe isn't just a static, silent stage. It is a vibrating, highly dynamic fabric. As astrophysicist Patrick Brady stated, an ocean of gravitational waves awaits. We have just barely dipped our toes into the water, and we now have this entirely new tool to explore the unseen depths of the cosmos. So what other invisible monsters and cosmic symphonies do you think are out there, just waiting to be heard? Keep wondering.